Today we're interviewing Päivi Törmä, I hope I pronounced that properly, Professor of Physics from Aalto University in Finland. And today you talk about quantum geometry and how it can explain a lot of different phenomena, things like superconductivity in flat bands, also some non-Hermitian effect in plasmonic lattices. But we would like to start this interview with the beginning, in this case of your scientific career. And especially what drove you to become a scientist and what drove you to choose physics in particular?
Well, actually, I didn't plan to become a scientist. I wanted to become a writer, writing novels and so on, but I thought I need some kind of job until I'm famous enough to give up my day job. So I chose physics because physics and math were both easy and interesting at high school. And then somehow I drifted into physics. It just took me, and I gradually stopped writing, except scientific papers.
Well, that counts as writing, I guess, too. So some people say that life is really like some stuck choices, decisions that we make along the way that really lead us to one point or a different other. So what would you say was the most pivotal moment in your career that led you to where you are right now, or moments? Should there be more than one?
I think here it's like two moments, but they are essentially the same. One is that I'm listening to a lecture as an undergrad, and after the lecture I feel the need of still sitting there and thinking that how should I understand this intuitively? And I felt that I'm the most stupid one in the class because others left, oh, it's clear, it's clear. And I was just thinking and thinking, forming some kind of intuitive picture, and then I was surprised I got the best grades from the exam. So, so I thought that I must understand this, otherwise it makes no sense to study. So then much later, when I was already a professor, I was in a conference and people were presenting this idea of flat band superconductivity, but I was thinking like, how do the electrons move there if it's flat? And there was some hand waving from some people, but I just don't understand. And I thought this is something that my group has to solve. And that led all to this quantum geometry stuff. So it's basically was in both cases that I let myself to be as stupid as I felt myself to be.
That's a good advice, it seems.
Yeah.
So you've mentioned quantum geometry, and that has been kind of like the center of your talk. Everything has gravitated around quantum geometry. So could you explain to us what is exactly quantum geometry and how it relates or differs from topological physics? Yeah.
So basically, in quantum mechanics, particles and other objects, they are described by their energy and the wave function. And physics has very much focused on looking at the energies, and that we can get everything from the energies. But quantum geometry is more about looking at the properties of the wave function. So how does it change when you change parameters and so on. And it relates to topology in the sense that if your quantum geometry is non-trivial, then it may be that also topology is non-trivial. So non-trivial topology always means also non-trivial quantum geometry, because topology is also about the properties of the wave functions.
Continuing on these quantum geometry questions, in a recent essay that you authored in PRL, and you also discussed this in your talk, you mentioned how quantum geometry explains why there is superconductivity in flat band superconductors, as you mentioned before. Could you explain to us how exactly quantum geometry explains this superconductivity? Is this a new form of superconductivity different from, say, the one explained by BCS theory or the high temperature superconductors?
Well, it's not completely different, but it's different, or let's say one has to look at properties that people have neglected before. So in some sense it has been there, but people have not looked at, because quantum geometric superconductivity becomes most prominent in flat bands, and there single electrons would not move at all. But when you form Cooper pairs, they actually can move, and that movement is possible only when the wave functions of the individual electrons overlap. And since quantum geometry is about the properties of the wave functions, it tells whether there is overlap or not.
So we have a follow-up question, is that why is this flat band superconductivity especially interesting for, as you mentioned in the talk, twisted bilayer graphene?
Well, in twisted bilayer graphene, superconductivity has been observed when the bands are quite flat. They are not completely flat, but they have very small bandwidth. And then all the theories that have been derived, assuming very dispersive bands, they may not be valid anymore. So one really needs to take this quantum geometry into account, especially if you want to have an accurate quantitative description. And there are already some experimental indications that probably we need to take quantum geometry into account.
So now, in your research, you do both theory and experiments. There are many examples of it, like the observation of, I think it was, sorry, I need to read this. The observation of non-emission effects in plasmonic lattices or the study of the dynamics of excitant power on condensates. Mm-hmm. So based on your own experience, also just as a theorist, then you drifted towards experiments. Mm-hmm. What advice would you give a theorist to have fruitful collaborations with an experimentalist, and also the other way around?
Yeah, so first of all, the understanding that it's really essential. Like physics is an experimental science, so any theorist must collaborate with experimentalists, and also in the experiments the understanding becomes much more deep when you work with theorists. So the first thing is communication. That communication is not easy. You have to somehow put conscious effort in explaining things in a way that you might not immediately explain, and seeing when the other one misunderstands, and a lot of patience in establishing the same language. And then I would also encourage a bit more skepticism about, so it's funny because I do both experiment and theory, how theorists usually they accept any experimental data. Look, yeah, this has been observed, and as an experimentalist I know that you get all kind of data, so one has to be cautious with it. And the same with theory, that for theorists it's always easy to explain almost anything because you can drop some terms from your formulas, and so one should be critical in a healthy way. And there is even an old joke that some experimentalists came to Landau, and so there was a plot like one axis here, and was telling, yeah, this is this quantity, and can you explain this? And Landau was looking, oh yeah, it goes like this, and then the experimentalist, sorry, the axes were the wrong way around, and then Landau, oh, then it's even easier. So yeah, these are my advices: good communication and a little bit of criticism.
So we're going to go a little bit off on a tangent with this question. It has to do with the relation between fundamental and applied physics. So John Bardeen, one of the fathers of BTS theory, was also instrumental in developing the transistor. Mm-hmm. So we have fundamental physics and also applied, more like engineering physics. So how easy it is nowadays for a researcher to do both fundamental and applied research? And is research nowadays too driven by the look for application?
Yeah, I mean, it's not too difficult to do both if you do them, let's say, around the same type of system material questions, because yeah, then you have the time to do it. If you choose very different applied research from your theory research, then it's maybe a question of time. And also nowadays we will need, if you do applied research, you will need some understanding of IP and so on. So your university has to have a good support for that. So, but otherwise I think it's completely possible to combine them, and they can come in sequence, like also in Bardeen's case when they invented transistor, they had a very clear applied goal, some better radio equipment. But Bardeen thought that, okay, on the way there, we first have to do some basic research about how electrons are screened and so on in semiconductors. And only then came the application. So they are very intertwined. And about the balance, I think nowadays it's quite good, the balance between applied and fundamental research, but sometimes people expect results too quickly from applied research. Like if there is a promising idea, it actually takes a long time to make it the real world.
So what is, in your opinion, the most beautiful phenomenon in physics, and also one that you still think of too challenging? I can't really get it. It's
superconductivity, obviously. Yeah, because it's first of all, example of when something becomes macroscopic and quantum. So it really has a macroscopic big wave function that is fully quantum, and it has enormously important applications, could be even more important in the future. I mean, I think that maybe our era will be viewed as the stupid era where people used electricity so that they all the time lose energy. Yeah, superconductors don't lose. And then it's a many-body problem, so it's intellectually very exciting. And now we have also this new additions of like spices of quantum geometry and so on. So I'm working on it very actively. And yeah, we understand superconductivity only in some systems, but in most systems we do not understand.
Yeah, like a theory for the high temperature ones is missing.
Yes,
So yeah.
Yes.
So in your talk, you also mentioned bound states in the continuum. These are very often mentioned when you go to a conference in photonics, but could you explain to us what exactly are these bound states in the continuum? Why are they relevant? And what's the importance behind them having these different topological charges?
Eigenstates of a system which are energetically inside a continuum. So the energy is somewhere where there are a lot of other states, but nevertheless they are decoupled from those other states. So for instance, in a photonic structure, it could be that that structure has some state with some energy, which is really within the radiative continuum. So in principle, energetically, the light could go out, but it doesn't. So it's like a dark state bound to this. The significance of this is that, for instance, when the states are bound into your structure, it can have very high quality factor, meaning like that it's a really good optical cavity. So then all light matter interactions are strong and lasing happens easily and so on. And then you may think that it's useless because the light can never come out. Well, you can make some small perturbations where this nice laser light comes out. And then the connection to topological charges is that if I have a bound state of continuum in some momentum, for instance, and in this kind of 2D systems, the momentum is usually connected to the angle where the light goes. So let's say in this momentum, I have bound state in continuum. That means that the polarization of the light around that momentum winds. And if it's winding, you cannot define what it is in the middle. It's the same as a vortex. It has a winding phase, so it cannot exist in the middle. So therefore, this middle point is this angle, so you cannot have any radiation there. So that's the connection between the topological charge and the fact that it's a dark state that doesn't radiate.
We are coming to the end of the interview. We'll finish with a couple of questions. The first one is, what is the best advice that you ever got that helped you in your scientific career? And the second one is, what is a piece of advice that you never got but you wish you had?
Mm-hmm. Yes, so for the first one, I think I was either a young postdoc or maybe an old PhD student. And in some conference, I asked from a professor that was from another country, but I somehow knew him a bit. Does he think that I'm good enough for scientific career? And I was expecting that either he says that, yes, of course, you are a genius. Yeah. Or he's saying kind of politely, yes, sure, but it's very difficult, which means you are not good enough. So he was quiet for a while. And then he said, yes, I think you should do a scientific career because you could survive in the system, but you would still make a difference. So this was a good advice because I understood that, okay, one part of it is in surviving in the system, like you have to publish in some kind of papers, journals, you have to get some kind of grants, and sometimes this almost takes all your energy, but you have to also keep in mind that in the end you are there to make a difference, to really choose what are the important problems, and maybe not the fashionable ones, but the really important ones where you can make a difference, and then take the risk to work on those. So this has been the best advice. And then coming to the second question, advice that I didn't really very clearly get, but I would give to others, that if you have a life partner who is also a scientist, you should make a big effort when you are young to get to a place where both of you can have a good scientific career. So it's very easy to go into some kind of wishful thinking that it maybe things will arrange by themselves, but usually they don't. So when you are young and mobile and so on, I would say search for a place which is pretty good for both, so that none of the people feels like, okay, my career was a bit compromised.
Okay, thanks a lot, Päivi Törmä.